And I'm here to present my lab on constant velocity and Newton's second law. To start off, I recorded this video of me rolling a tennis ball across the floor on what I tried to keep as straight as axis as possible. Then next I moved the video into Tracker and, following the instructions from the PowerPoint, marked each point and created an axis. I went frame by frame, trying to click in the center of the mass of the ball, and took about 30 frames worth of data. Alright, it's finishing up. And as you can see, my y-axis wasn't perfect. Kind of drifted over it a little just because of the camera angle I shot at, and the ball rolled further back a little, so the data wasn't perfect, but it was close. Next, I used the skeleton code given to us online and edited it to make a model of what the tennis ball's motion should be if the net force on it was 0. I changed the mass of the ball, I changed the position, the start position of the ball's initial velocity, which I found using Tracker, and I also changed the end time along with changing the velocity equation to fit that of Newton's second law. And of course I also changed the net force to 0. Using the data extracted from the model and the data found using Tracker on my experiment, I created the chart you see now. As you can tell, my experiment didn't match the model perfectly. My experiment showed signs of deceleration, likely due to friction between the ground and the ball and the air friction on the ball. The change in velocity shows that the net force isn't 0, and since it is not in an ideal system, keeping the net force 0 is almost impossible on a flat surface. So to wrap up, I'll go over a couple questions. For the first question, since I chose for the ball to roll along the x-axis in the positive direction, the velocity is positive. And if I'd flipped the axis and chose to have the ball move in the negative x direction, the magnitude of the ball's velocity would have been the same, but in the negative direction. So just to re-emphasize the reasons behind the differences between the experimental and predicted data, they likely stem from friction forces acting on the ball to slow it down, and the ball not perfectly staying on the x-axis. Thanks for listening along with me today, guys, and I hope this presentation was informative for y'all.